Welcome to today's Explainer. I am so thrilled to have you here because we are unpacking some seriously exciting AI news today. Look, if you've ever built or deployed large language models in production, you know the absolute headache of inconsistent outputs. Well, today we are diving into a groundbreaking research paper that completely flips the script. Instead of begging LLMs to directly synthesize answers, this new approach trains them to generate zero-shot structured workflows. It's called MetaFlow, and honestly, it is going to completely change how we think about automation. Let's get into it. Okay, here is a quick look at our roadmap for today. We'll start with 1, the LLM consistency problem. Then 2, the MetaFlow's paradigm shift. 3, the two-stage training pipeline. 4, evaluating zero-shot generalization. And finally 5, the impact on developer tooling. Don't worry, we are absolutely going to connect all this heavy theoretical architecture directly back to practical, everyday developer applications.
All right, Section 1, the LLM consistency problem.
I want to pose this question directly to you. Why do LLMs actually need structured workflows instead of just giving us direct answers? Think about it for a second. Right now, asking an LLM for a direct answer is basically asking it to guess the final result token by token. It's kind of like trying to bake a really complex cake by just throwing all the ingredients at a wall, rather than, actually writing down and following a step-by-step recipe.
The thing is, direct answers are incredibly instance-specific. They're a total black box, and they completely lack the structural consistency you absolutely have to have for reliable production deployment. Structured workflows fix this. They decouple the reasoning patterns from the specific data instances, which gives you deterministic, interpretable execution traces. If something breaks, you can debug the exact step that failed. And even better, these workflows encode recurring algorithmic patterns that you can just reuse across related problem sets.
Moving right along to Section 2, the MetaFlow paradigm shift.
Let's trace how workflow generation has evolved over time. We started way back with manual design, which, requires massive domain expertise and scales incredibly poorly. Then we moved to task-level search. This used methods that needed costly, from-scratch optimizations for every single new task. We're talking sometimes thousands of API calls. Then came instance-level generation, dynamically creating a workflow for every single query, which is just wildly redundant. Now, we are entering Phase 4, meta-level generation. This is what enables true zero-shot generalization.
So the crucial point here is how MetaFlow reframes this whole process. Instead of just predicting a final answer or doing some expensive search loop, the model receives a task description and a predefined set of operators. Things like generate, summarize, or decompose. It then literally learns to compose a solution strategy. This gives you incredibly fast adaptation without any gradient-based fine-tuning at inference time. It just synthesizes the right sequence of operators right there on demand.
When you stack these approaches up against each other, the pain points of the older methods are so obvious. Task level relies on an expensive search loop, and instance level redundantly creates unique workflows over and over. But MetaFlow sits perfectly in the middle. It synthesizes a reusable task-level workflow from a description with just a single model inference. Think about that. Just one forward pass and you have a completely reusable workflow. The computational savings here are absolutely massive.
Okay, Section 3, two-stage training pipeline.
Under the hood, MetaFlow is trained in 2 distinct phases. Phase 1 is supervised fine-tuning, or SFT, on synthetic workflow data. This is a big deal because it teaches the model basic syntax and logical chaining. Essentially, it gives the model a cold start so it knows how to write syntactically valid operator calls. By getting that baseline out of the way, it shrinks the search space. That means Phase 2, reinforcement learning with verifiable rewards, can focus purely on optimizing how effective the workflow is rather than, struggling to learn basic Python syntax.
During that second phase, the model actually executes its generated workflows across multiple problem instances. This execution feedback acts as the reward signal using the GRPO algorithm, which essentially scores different workflows against each other to optimize the policy. And what's absolutely vital here is a variance reduction technique called common random numbers, or CRN. By evaluating all candidate workflows in a batch against the exact same set of problem instances, they basically eliminate background noise. This quickly prunes out ineffective sequences and reinforces the really solid execution paths.
If there is one key takeaway from the training architecture, it's this. The system explicitly evaluates based on verifiable correctness, not just token-level likelihood. The reward only comes from whether the workflow actually solved the problem when it was executed. This ensures that the learned strategies are completely functionally sound before they ever reach deployment.
Moving into Section 4, evaluating zero-shot generalization.
Looking at the benchmarks across math, reading comprehension, and code, MetaFlow nails a highly competitive 78.8 average score. Now yes, it does slightly trail ScoreFlow's 82.5, but you really have to consider the cost difference here. ScoreFlow requires resource-heavy per-instance optimization for every single query. MetaFlow does this with a single inference pass. You generate the workflow once, apply it to the whole task, and completely eliminate that per-instance overhead. It's a game changer.
Of course, dropping in totally novel operators out of nowhere does carry some inherent risk. You'll actually see average scores drop significantly at first because those novel scenarios often trigger syntax errors. But because generating a workflow only costs a single inference, you can easily just sample a few dozen variations. This best-of-case selection strategy proves that with just a moderate number of samples, the best workflow easily blows past the baseline, super efficiently identifying highly successful solutions. And that leads us to this honestly staggering number, 60.9%. That is the accuracy improvement MetaFlow achieved over the baseline on the Hotpot QA multi-hop reasoning dataset. And the craziest part? It did this by synthesizing a complex workflow using a totally novel vector search operator that it had never ever seen during training. It literally just read the natural language description of the operator and figured out how to orchestrate a sophisticated multi-hop retrieval and reasoning cycle all on its own. Now that is true zero-shot generalization.
Finally, let's wrap up with Section 5, Impact on Developer Tooling.
So what does this actually mean for us? Here are your actionable next steps. First, keep in mind this is a research prototype right now, so you'll want to track the archive repository for official code-based drops. When you do start testing this, make sure to isolate your operator set so you can accurately measure that zero-shot transfer. You also need to get your infrastructure ready for verifiable rewards, meaning containerized execution environments and deterministic operator definitions. And finally, while single inference cuts API costs massively compared to iterative search, remember that multi-step agent chains still introduce latency and failure propagation risks, so monitor those boundaries carefully. I want to leave you with this final, really powerful thought from the research. Treat the model as a strategy composer, not a drop-in replacement for direct inference. MetaFlow really invites us all to rethink AI architecture. Instead of just begging a model for the right answer, we should be empowering these models to write the reliable, reusable rules to find the answers themselves. So how will you compose your next automated system? Thank you so much for joining me on this explainer, and as always, keep building.